Yes? Okay, this is working. Welcome to all of you. It's 2:30. Welcome to the fifth session of the Symposium on Hydrogen Embrittlement. My name is Tom de Pover. I'm from Ghent University. And together with Professor Koyama, I will be chairing this fifth session. Since it's the opening of the final session with the talks, I also want to tell that tomorrow evening and the late afternoon, we'll have some roundtable discussions with 4 talks, and also then with an interactive discussion with all of you. So you're very welcome to join, because that session will close the thematic symposium on hydrogen embrittlement. So it would be very nice if all of you can attend that session, the roundtable discussion, tomorrow evening. So at the end of the presentations, I will give some more information of the contents. But for now, I think we can continue with the first invited talk of this afternoon. This is from the group of Yann Charles, and the presenter, I'll have to take a look here. The presenter will be, if I'm not mistaken, is Bian. Yes. So please, the floor is yours.
Thanks for the introduction. My name is Xavier, a PhD student from LSPM laboratory in University Bonnin. It's a great honor to present you our work on hydrogen transport in a multi-material component under complex thermomechanical loadings by finite element modeling. First of all, I'd like to introduce you the ITER, which is an international nuclear fusion research and engineering project. There exists a plasma flow in the fusion reactor named tokamak, containing some isotopes of hydrogen, deuterium, and tritium. Because of the radioactivity of the tritium and the effect of hydrogen embrittlement, so it's necessary to pay attention to the hydrogen retention in the material and the disposal of the tritium containing of the waste of water. In our present work, we focus on the devoter, which is a main plasma phasing component. The devoter consists of monoblocks, and each monoblock is constituted of tungsten, a copper interlayer, and a copper zirconium cooling pipe with a water flow inside. Our model is based on a monoblock subjected to plasma flow at its top surface, and our objective is to evaluate the hydrogen retention in the monoblock and the hydrogen permeation towards the cooling pipe. I will start with modeling processes, then the numerical implementation, and the last some applications, and the relevant results will be shown. The plasma flow contains an intense hydrogen flux, and the hydrogen atoms can penetrate through the top surface of the monoblock and diffuse inside. In the meantime, they can be also trapped by the material defects like vacancies, dislocations, grain boundaries, and so on. The hydrogen flux induces also a high heat flux. That's to say, we have also heat transfer inside the material with thermal expansion and plasticity, especially at the material interfaces. Last, we have also a variable temperature and a uniform water pressure due to the water flow in the cooling pipe. So what we face is a highly thermomechanically coupled problem. To solve the heat transfer is resolved by the heat equation. The thermal expansion and the parameters for the elasticity are listed here. And we assume that the plasticity is dominated by the isotropic hardening. The hydrogen is usually expressed in terms of concentration, and this concentration can be divided into 2 parts, the diffusive one and the trapped one. The diffusion equation is based on the Fick's law. And we have also added the impact of the hydrostatic stress in this formula. For the trapping equation of hydrogen, is based on the McNabb and Foster's equation, which describes a transient trapping process. Because of the difference of the solubility for the three materials of the monoblock, some researchers have proposed a boundary conditions like the continuity of Cl over S, and we have also taken this assumption in our modeling. For the isotropy hardening curves have been identified from the literature and provided by ITER intern documents. And we assume that there were two kinds of traps in the tungsten, and a unique kind trap in copper and carbon zirconium respectively. And especially we have proposed our own creation law for the dislocations with respect to the plastic strain according to the data from literature. The core content of our work is numerical implementation with some user subroutines of Abacus. For example, we use UEL to create a new degree of freedom for the temperature, and the temperature is calculated at each node of element, and then we pass the temperature to all the other user subroutines of Abacus. For example, DISP is used for defining the boundary conditions, for example, the heat flux or the Cl over S, and we use the Cl, the hydrogen concentration, instead of the particle flux for the sake of simplicity. The U expand is for the thermal expansion. UMAT is used to resolving the thermal mechanical behavior of material. The transport and trapping of hydrogen, as well as the continuity of Cl or S are implemented in UMAT THT. The important thing is that all these processes will be resolved at the same time. We can just construct a quarter of monoblock thanks to its geometry symmetry, and over 19,000 linear full integration elements are used for the mesh. We have also refined the mesh for the copper interlayer and the zirconium cooling pipe to obtain a better simulation result. Here represents the scenario of plasma loading. This scenario consists of three phases. The phase one corresponds to the continuous plasma exposure, and the phase two is the baking phase to remove the hydrogen from the monoblock, and the last, the phase three is a maintenance process with a lower constant temperature in the cooling pipe. We have imposed a constant thermal flux of 10 megawatts per square meter at the top surface, and it stops at the end of phase one until the end of the whole simulation. For the temperature of the cooling pipe, it varies like this. For the hydrogen loading, we have imposed a constant hydrogen concentration at the top surface, and it stopped at the end of phase one and then keeps zero until the end of the whole simulation. Here represents some results. We can see that the hydrogen accumulated with time during phase one and stored mainly in the zone of tungsten. And the temperature field is listed here. We have also done a simulation of hydrogen retention for all diverters in the tokamak was around 10 micrograms. We can see that a mismatch of thermal expansion at the material interfaces and induced the plasticity in the same zone. And due to the plasticity strain and the temperature gradients, the hydrostatic stress field was like this. During phase two, the hydrogen was removed from the monoblock because of the high temperature in the cooling pipe, and at the end of phase 2, there was only 0.3% of hydrogen remained mainly in the half upper part of tungsten, and moreover, around 57% of hydrogen have passed into the cooling pipe. During phase 2, we can see that there's nothing to do with the hydrogen retention or the hydrogen flux towards the cooling pipe, because the maintenance temperature in phase 3 is too low to have impact on them. In fact, the plasma loading is not continuous. For example, an executable scenario of the ITER plasma operations is like this, which represents 13 plasma processes per day. For the sake of simplicity, we have taken a concatenation of 3 days of ITER plasma operations during 16 months as our cyclic case compared to our continuous case. And I'd like to show you about the hydrogen retention and the plasticity. In the first figure, we can see that we have reduced around 3/4 for the hydrogen retention for the cyclic case compared to the continuous case, and the plastic strain, for example, at point B, kept increasing during the whole phase 1 for the cyclic case, because the plastic strain is driven by the thermal expansion. That's why the plastic strain for the continuous case remains constant, because we have no variation of the temperature, no variation for the thermal expansion. However, the cyclic case makes a cyclic variation for the thermal expansion, and induces a cyclic variation and induces an impact on the hydrostatic stress distribution in the monoblock, and thus on the transport and retention of hydrogen in the monoblock. The conclusion is that we succeeded in making a numerical implementation with some abacus user subroutines to solve such a highly composed problem, and in realizing some applications on industrial components, we are able to make an estimation of hydrogen retention and the hydrogen permeation inside the material. Of course, our assumptions of model are not complete. There exists, for example, the cyclic fatigue, the material damage, or the recrystallization of metal, etc. So for this, we keep an open mind to improve our theoretical model. Thanks for your attention, and if you have any questions.